The Cigar Lab, part of the Department of Computer Science at North Carolina State University, presents Semi-supervised classification of static canine postures using the Microsoft Kinect. To facilitate canine-computer interaction, there are a number of potential interaction methods, such as on-body sensors and nose-actuated buttons. Some caveats to these methods are training the dog to become accustomed to wearing the sensor and actuating the apparatus. Another approach is to use the Microsoft Kinect to watch what the dog is doing. As first steps towards this interaction method, we have developed an algorithm capable of identifying when a dog is standing, sitting, and lying down. The first step is to take multiple images of the background. The multiple images are then combined to reduce the noise in the depth data returned by the Microsoft Kinect. A dog is then introduced into the scene. To build the model for the semi-supervised classification, 5 images of him standing still must be obtained. Since the Kinect captures at 30 frames a second, this takes a very short amount of time. For every image, the background is subtracted, leaving only the dog in the scene. Contour detection is used to isolate the depth information of the dog. The algorithm uses 2 pieces of information to classify the posture: the distance of the dog from the Kinect, and the aspect ratio of the bounding box around the dog. Since we know the distance when the dog is standing, we can assume that the dog is lying down when he appears farther away. When the dog is standing, the bounding box around him is more rectangular, but when he sits, it becomes more square. Using a simple decision tree, we can classify the dog's posture. To evaluate the algorithm, we had 5 dogs go through a series of standing, sitting, and lying postures. For each dog, we captured 10 seconds of video with the Kinect, which equates to 300 frames. We then had 5 volunteers analyze the captured video, independently marking the frames with the dog in each posture. We used that data as the ground truth when evaluating our algorithm's performance. The algorithm's overall accuracy was 83%, successfully classifying a stand 70% of the time, a sit 69% of the time, and a lie 94% of the time. Most of the time, we found that the algorithm classified a posture within 14 frames of the ground truth, which equates to just under half a second of latency. Previous studies have found that when training a dog, the latency between a dog performing an action and the reaction to that action must be less than half a second, which indicates that our algorithm is potentially fast enough for training applications.